Welcome to today's webinar. The topic today is modeling of sections in R section 1. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the Dlubal website, the German and English webinars, and the newsletters and so on. I will be the moderator today and will answer your questions together with Markus Baumgartel. Sonja will do the presentation, but my two colleagues can introduce themselves.
Hello, I would also like to welcome you to today's webinar. My name is Sonja von Blue and I will be the presenter today.
Hello, my name is Markus Baumgartel. I'm responsible for customer support and frequently asked questions on our website. And today I will help Sonja to answer your questions during this webinar.
Okay, thank you for your introduction. You can ask questions via the control panel on the right side of your screen. Just show or hide this control panel with that arrow here, and then you can enter your question here. We will answer you, and if you don't get an answer because there are too many during the webinar, you will get an email afterwards. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. To the agenda today, at first, Sonja will create cross sections using a DXF template. We will show 3 different options. And in the next step, she will create cross-section using a block and using also JavaScript. Okay, before I hand over the screen, just a hint. Please visit our booth at the Bau in Munich. And if you book a live demo, then you will get a free ticket. Just click on that link here or scan the QR code. At the end of the webinar, I will show where you can find the PowerPoint slides, and then you can use the link or the QR code. Okay, that's all for the introduction. I will hand over the screen to Sonja. Sonja, it's your part.
First, I want to show you how you can use DXF files for modeling. I import the DXF file via File, Import, DXF. Then I have to select the corresponding DXF file, click on Open. And now in this window, you can specify the insert point here in this area and the rotation. It's also possible to do a coordinate transformation in this area. And in addition, if you have very short lines in the DXF file, it's possible to minimize the tolerances. Furthermore, I can define the length unit of the DXF template. Furthermore, the material must be defined for the automatic generation of the cross section. In this section Create R section model, you have 3 options for creating the cross section. I would like to demonstrate this to you with examples. The functions create elements automatically and use DXF template lines as center lines, already create parts and elements. Elements are required for the calculation using the thin-walled analysis and for the calculation of the effective cross-section, since only then the subpanels are available. The subpanels are required for the classification and calculation of the effective cross-section. If no elements are defined, the cross-section is treated as a class 3 cross-section in the design add-ons. The automatic creation of elements is useful if the outlines of the cross-sections are available in the DXF file. I will show you a DXF file for this. Our section then creates center lines between these parallel lines and then set the elements between the intersections. Only elements that do not exceed the maximum thickness that you can define here are created. I define here a maximum thickness of 2 millimeters. Then I have to define the material. For this, I open the material library, and then I look for the desired material, and I choose this. And after this, I click on OK, and the cross-section in the DXF file will be imported. Now, the parts and also the elements are created automatically from this function. You can call this function also here in menu edit. You find it here in manipulation, create elements automatically. So you can call this a function also afterwards, or if you have a file with parallel lines, you can create then the elements automatically. I would now show you the create elements on center lines function. For this, I open the import dialog again. So I go on File, Import DXF, choose the corresponding file, and click on Open. This import function is useful if the cross-section geometry is available as a centerline model. You can now see such a model here in this image. The lines of the DXF templates are considered as center lines of the elements. The thickness that you can define here will be assigned equally to all elements. I define here a thickness of 2.75 millimeters, and then I have to define also the material. For this, I open again the material library via this button, look for the wished material, and then I import this DXF file. Here again, the parts and the elements are created automatically. It's also possible to use this function afterwards. You find it in a menu edit. Here again, in manipulation, create elements on lines. If you have a file with lines that acts as center lines, you can create elements on it. As a third import option, I would like to show you the function create DXF template. To do this, I open the import dialog again, choose the file, and then I use this function. With this import function, the lines in the DXF file are imported as lines. You can then use these lines as an aid for modeling. This function is useful for massive cross-sections where no elements need to be created. In addition, this function can also be used for complex cross-sections where I only want to create elements for the decisive cross-section part. I would now create such a cross-section. Then I click here on OK. Then the DXF file will be imported. And then I have to create the part. To create the part, I use the function select boundary. And here I have also to define the material. I open the material library again and look for this material. It's an aluminum material. Click on OK, OK. And then I have to select the outline where I want to create the part. And the part will be created. Then I have to create the openings. For this, I use the function select boundary for openings again. And then I click on the corresponding lines. Since a classification is to be carried out and the effective cross-section may have to be calculated, elements must be defined. With this cross-section, I only assume these webs here as being at risk of local buckling. So I define elements for the webs. I also create elements for the flanges here because only then the support of the subpanels are created correctly and the elements are connected to each other. To create the elements, I first create the center lines. For this, I can use a function that I will find in menu tools, modify lines, set center lines. This is a new function that will be available in the next customer version. The only thing that I have to do now is to click on the lines where I want to create the center lines between these lines. So I click here on these lines. The lines now have not the correct length. To create the correct length, I use another function that I can also find in the Tools menu, Modify Lines, Create Round Corner. To create sharp corner, I define a radius of 0 millimeter, and then I have to click on the corresponding lines. Now I want to know the element thickness that I have to create. So for this, I choose the dimensioning tools. I choose here the linear dimension, and then I choose this point here. In this point, the projection in Z direction, I see here, okay, this has a thickness of 1.6 millimeters. I do this also for the webs. The webs have a thickness of 1.8 millimeter. And again, for the lower flange. And this has a thickness of 1.5 millimeter. To create now the elements, I use the function that I mentioned before. You can find it in the menu Edit, Manipulation, Create Elements Online. First, I create the webs. So I define here an element thickness of 1.8 millimeter, and then I select the center lines and click on Apply. For the upper flange, I define a thickness of 1.6 millimeter and choose the line, click on Apply. And for the lower flange, 1.5 millimeter, and I choose here the line. Then I want to choose the finite element analysis. To do this, I open the base data dialog. Here, the analysis method finite element analysis is already chosen. This analysis method is then used to calculate the cross-section based on the parts. This is important because otherwise the cross-section values such as the torsional moment of inertia or the warping resistance, which are only calculated over the defined elements in a thin-walled analysis, are too small. So I have to choose this finite element analysis. The effective cross-section is always calculated analytically. In the calculation of the cross-section values, the cross-section part in which there are no elements are also taken into account. I want to determine the effective cross-section, so I activate the checkbox effective section and I choose the Eurocode 9 standard. I want to neglect the additional bending moment due to the shift of the centroid, so I go to Tab Settings and Option, and then I activate the corresponding checkbox. Then I have to define a load case. I will do this now. So I choose New Load Case. I can give the load case a name. I call it N. Click on OK, and then I have to define the internal forces. New internal forces. And here I define a pressure about -1 kilonewton. I start the calculation now. And then I will get two results. I will get the results of the gross cross-section. I can choose it for the graphical output here. It's a finite element analysis. Then you can see the stresses and unit stresses and so on the gross cross-section. And the numerical output is here in this table. There I can choose also the finite element analysis. Again, these are the results of the gross cross-section. if I want to see the results of the effective cross-section, I have to choose here effective thin wall analysis. Then I get the section properties, and I also get the section classification. And as I can see here in the table, the section falls into class 4 as expected. I can see here also the subpanels. And if I click onto this subpanel, I see, okay, this subpanel is classified as class 4. And I can see the details of the classification. And it's also possible to see the reduced thicknesses of this subpanel. I can see here the effective thickness and the intermediate results. And it's also possible to output the effective cross-section graphically. And if I zoom into this, I can see here the cross-section thickness is reduced. A new file is created during the DXF import via the dialog that I showed you before. If I want to import DXF files into an existing file, this can be done via a new background layer. You can find this function here in the navigator data in a guide objects, a background layer, and then I can here create a new background layer. Okay. This brings me to the second topic of this webinar, the blocks. In our section, you have the option of saving object groups as a block and then reusing this block. The blocks are managed in the Dlubal Center blocks that you can open here. In the Dlubal Center blocks, there are many cross-section available during the installation. There are 3 block types in our section. These are blocks without parameters, then blocks with parameters, and blocks with JavaScript. I would like to show you all block types. In case of a non-parameterized block, the cross-section has been created without parameters. As a simple example, I create a flat bar. So I create a new model. I give it the name flat bar. Click on OK. And then I will define the element. I will define it graphically with this option, single. I use the input mode length and direction. I now want to reverse the orientation and want to define the angle on the work plane about 90 degrees. Then I define the length, 50 millimeters, and the thickness. Now the part here is created and also the element. I will dimension the length and the thickness of this flat bar. So I use these functions again, linear dimension. In order to save the structure or partial structure as a block, it must first be selected. I want to save the entire structure as a block. So I select now the entire structure. Then I save the function save as block. And in this new window, I have to define the block name. I name it block without parameter. And then I enter the block classification in this window. And this block classification serves as a filter so that I can find the block more easily. And a few categories have already been created here, and I choose the category thin wall section others, and then I click on OK. The block can now be inserted into any file, and I want to insert this block into the same file. To do this, I open the Dlubal Center blocks, and then I select the block that I have created, the block without parameters, and click on OK. In this tab main, I can set the insert point of the block by choosing the insert point in the graphic. Maybe I can choose this insert point. It's also possible to use this drop down to choose the block point. And it's also possible to define the position. I can write it directly into the input fields, or it's also possible to choose it in the working window with this button. And then I go to the tab structure. Here I have the possibility to change the material. This information was read from the cross-section that I saved as a block. I don't have any other settings now, so I can click on OK to insert this block into the file. The block reference is not lost. If I go to Navigator Data, I find in the tree special objects the blocks, and here is the block, and it's possible to double click on this to open the edit window, and here I have the possibility to change the position or the insert point. So maybe I can change it here to 60 millimeters, and then this block will move in the working directory, in the working window. And I have also the possibility to use the function that are in our section. So I can use also the move copy function to move this block here, maybe 20 millimeters. And I can also use here the rotate function and so on. And it's also possible to convert this block into normal geometry. And if I do this, then the block reference is lost, and I can modify all the objects of this block, like the points and so on. Okay, I will delete this block. I don't need it anymore. I want to show you now the parametric block, and for a parametric block, the cross-section has been entered in such a way that the topology depends on parameters. In addition to the geometry, internal forces can also be parameterized. I'm going to add parameters to the flat bar I just created, and these parameters can be set in the global parameters window. I can open it here, edit global parameters. Each table row manages a parameter. The name of a parameter must consist of ASCII characters and no spaces are allowed. The parameter is addressed in the formulas via the name, and each name may only be assigned once. The unit group of the parameter is to be selected in the list. This determines whether the parameter represents a length, angle, or something else. The unit groups are organized by category in this list. I choose here length. The definition type controls whether the parameter is described by a value or by a formula. Depending on your selection, you can enter the value or the formula in the following columns. First, I create a parameter with the name DL for the length, and it has the unit group length. It's from definition type value and has a value of 50 millimeter. Then I create a second global parameter called dt for the thickness, and it has also the unit group length and the definition type value and has a value of 10 millimeter. And I click on OK. I now define the point coordinates depending on these parameters. For a better overview, I show the numbering of the points. For this, I go to the navigator display and activate the checkbox numbering. I only want to see the numbering of the points here, so I deactivate the other check boxes. Then I define the points, and the first point that's here, it has the current coordinates 0, 0. This is okay. The second point has the coordinates 0, and in the set coordinate is equal minus DL. The following coordinate has the y coordinate equal dt. Divided by by 2. Also the next coordinate equal dt divided by 2. Z coordinate is equal minus dl. Next coordinate is equal minus dt. Sorry, equal minus dt divided by 2. Equal minus dl equal minus dt divided by 2 and 0. The thickness of the element must also be defined with the parameter. So I go to the tab Elements, and here I define the thickness equal dt. I now want to show you what's happening if I change the parameters. For this, I open the Edit Global Parameters window, and then I change here the value of the length to 40 millimeters and of the thickness to 5 millimeters. if I apply these changes, you can see now this cross-section is modified by this global parameters. I can change it back to 50 millimeter and 10 millimeter, and then I apply the changes. If I now want to save the cross-section as a block, the structure to be saved as a block must be selected. So I select now the whole structure, then I click on File, Save as Block. I give the name block with parameters, and the block categorization. Here I choose also thin wall sections, others, and then I click on OK. I open now this created block with parameters. I click on OK. Here in the tab main, I have the same possibilities like for the other block, but here in tab structure, I have next to the possibility to change the material, the possibility to change here the defined parameters. I will do this. I define here 40 millimeter, and then I select the insert point here, and then click on OK. The mapping to the global parameters is lost when inserting the block. However, I can change the parameters defined in the block at any time. I can open this block here if I double click on this entry, and then I can change the parameters, but they are not combined to the global parameters that I used for this flat bar. I can show you this if I edit now the global parameters here, maybe to 60 millimeter, and if I apply the changes, then only the flat bar on the left will be modified, not the flat bar on the right. But this is also possible that I apply the global parameters to the block parameters. To do this, I open the block again, go to structure, and then I define here the global parameter DL and the global parameter DT. If I now edit the global parameters, here maybe the thickness of the elements, and click on OK, I can see that the modification is done in both cross-section. This brings me to the third block type, blocks with JavaScript. Here I have the advantage that I can add or delete structure objects. This is not possible with a parameterized block. For example, I can add a second element in a block that I've created only from one element. I won't need to save the block with two elements. However, this is possible with the blocks that use JavaScript that I want to show you now. With scripting, it's possible to create the topology, the load cases, and the internal forces. For the creation of script files, you only need an editor like Notepad++. The documentation on blocks with JavaScript can be found on GitHub. I will show you this. Here you see an overview of a function used for blocks. And the three main functions are the function global parameters, input data, and generate. The global parameters function is used to create global parameters, which, as I have already shown, can also be used on the blocks. The global parameters function is not used in my script file. The input data function is used to create the input table in the block dialog with input parameters, and the generate function is used to generate the blocks. Input variables added in the input data function can be used in this function. I will now create a JavaScript file to generate the flat bar that I've already presented. I've prepared the JavaScript here, and I will show you the function input data first. And in this input data function, a category can be created in the blocks input table using the category function. The categories geometry and materials are created here. The input parameters DL and DT are created here in the category geometry. In the generate function, I open it here, the points, the lines, the part, and the elements are generated. A list of the available JavaScript commands can also be found in GitHub. I open it here, and you can see here all the JavaScript commands. I open again my JavaScript file, and then I want to explain how to create points. Here I create the points, and you can see here the description on GitHub. To create a point, I have to use this point. Then I have to define the number of the point, and then the coordinate Y and the coordinate Z. I do this for my 6 points. It's like for the parameterized input. I use here the variables that I can input here in this input data. Then I create the lines. For this, I create the line and then a function to set the parameters of the line. So here I set the line with number 1, and this line is from point 3 to point 4. The second line is from point 4 to point 5. Then I will show you the creation of the parts. Here I create the parts, and here I create the part via the boundary lines. The boundary lines are the 4 lines that I've created here. Then I have to define the elements, and for this I create the elements first, and then I create a function to set the parameters of the elements. And here I set the line elements, and I create here the element 1, and this is from point 1 to point 2 with a thickness of dt, and dt is the variable that I can define here in this parameter. To create the block now, the function for creating a block can now be called in any RSECTION file. The file content is not used. So I open RSECTION again, and then I choose in File, Save as Block, and then I will name the block with JavaScript. I choose the block category thin wall section others, and now I have to choose the JavaScript file that I've created and shown you before. And then I click on OK. To invert this block, I can open the Dlubal Center blocks, and then I choose this file here, click on OK, and then I can define the length and the thickness, and I have also an overview of the JavaScript that I've shown you before. The advantage of being able to add structure objects is not apparent in this simple example. I would like to show you this with a more complex example of a U section. And the U section should be able to be created with and without a specified number of screw holes. I open for this the corresponding JavaScript file, and here in function input data, I use here a parameter int to create an input parameter I number of the data type integer. This is used to dynamically create the number of openings. Under the category geometry, I create also the input parameters DE for the distance and the input parameter DD for the diameter of the opening. And both parameters are created dynamically via the multiplicity counter I number. That's here. I had already imported this JavaScript block, and I will show you this here. I create a new block and I choose this block now. And if I now here go to structure, I have here the possibility to define the height, width, and thickness. You can see here also this cross section that will be created in the graphic on the right. And here I have also the possibility to hide the numbering. Here I can modify the height maybe to 250 millimeter. And here I have the possibility to modify the number of openings. Now the cross section is created without openings, but I have here the possibility to add an opening, and for this I have to define the distance E1 and D1. You can see it here on the right, what's E1 and what's D1. So I can modify this a little bit, maybe to 20 millimeter, and I can show you the dimension with values and not with symbols. And I have also here the possibility to add just more openings. That brings me to the end of the webinar. I hope it helps you working with DXF files and blocks. I now give the floor back to Andreas.
Okay, thank you, Sonja, for this nice presentation. I think the attendees could see how easy it is possible to create cross sections in our sections. Just download our trial version if you don't already work in our section. I would like to hand over the screen again, just a moment. Again, the hint for all attendees who participate later in the webinar, if you want to visit the BAU and want to have a product demonstration on our booth, just book a live demo, then you will get your free ticket. You can click on that link or scan that QR code. If you don't visit the BAU, you can book your free online appointment. You can have a free product demonstration or an offer for our products. You can click on that link or scan that QR code. It's up to you. I would like to show where you can find the slides, that you have the links and so on, and where you can find the files and the recording. Just a moment. That's our website, dlubal.com, and under news and events, you can find the webinars. That's today's webinar, and those are the webinars for the future. Next webinar is about form finding, then a definition of construction stages, and so on. So I click on that webinar. That's today's webinar. In the next days, you will get an email with the link to that page here. You will find the recording here in the middle. Then you already find the presentation slides here and the DXF and JavaScript files here. And at the bottom, you can find our section files. Okay, that's also all from my side. I thank you for your attention. Thanks to Sonja for this nice presentation. Thanks to Markus for his help answering the questions. I wish all a nice rest of the day. Maybe a last hint: when you leave the webinar, there's a small survey. You can score the webinar. It would be very nice. It takes you about 1 minute, I think. Just note that the worst score is 1 and the best score is 5. You can enter your wishes for future webinars, but you don't need to do that. Just enter a sign, minus or so, or leave it empty. Okay. I say bye-bye. Maybe we meet each other in the future webinar. Again, have a nice day.